Hello, let's start section 3.4. 3.4 is limits at infinity. Then why limits at infinity? Why we are studying limits at infinity? One of the reasons is here, which we call it horizontal asymptote, correct? When we do some limits, easily we can find a horizontal asymptote. Before discussing horizontal asymptote, let's recall chapter 1. Some topics of chapter 1 that I discussed with you, I wanna go over them again here. Then we will jump to horizontal asymptotes. Remember when we had like limit of f of x as x approaching to a number a, it can give you a positive or a negative infinity, correct? Also, we discussed in chapter 1, at the beginning of the chapter 1, when I had a review on the functions for you, I talked about discontinuity. Discontinuity, right? And I and S. What is discontinuity? Remember, if you have a function, for example, f of x equals x minus 3 over x squared minus 9, there is a discontinuity in this function, correct? Because you see, your denominator cannot take 3, right? If even I factor this, the factor of the denominator is x plus 3 and x minus 3, right? If you plug in 3, the denominator becomes 0, correct? That's why we call this function has a discontinuity, but this one is a removable discontinuity. If you remember from chapter 1, because you have in the numerator x minus 3, denominator is x plus 3 times x minus 3. You can cancel out x minus 3 with x minus 3 and you end up with 1 over x plus 3, right? We call this one a whole. Remember, we called it discontinuity, that the function has a whole. And where is the whole? The factor that you cancel, that is your whole. At x equal 3, this function has a whole, correct? Or this example, for example, f of x equals x over x plus 2 times x minus 1. It's a rational function, correct? Even you cannot cancel anything. For some values of x, your denominator becomes 0, right? If I put x plus 3, x plus 2 times x minus 1 equal to 0, from here x equal negative 2 and x equal 1. These are the discontinuities of the function, and actually we name them vertical asymptote, right? When you set the denominator equal to 0, you get vertical asymptote. We call this one also discontinuity, and we call them vertical asymptotes because they are not removable, right? Then when we discuss discontinuities, we are dealing with two cases. Case number 1, you get a whole, like what I explained in example number 1, right? Like this one, you get a whole, correct? But whole, we call it removable discontinuity. Case number 2, you get a vertical asymptote. Right? When you get a vertical asymptote, usually when you are dealing with a rational function, And how you find the vertical asymptote? Always remember this. Denominator equal to what? To 0. We set our denominator equal to 0 and it gives us the vertical asymptote, correct? Now, let's do an example on these and link it with the limits. Then after that, we jump slowly through the finding horizontal asymptote, correct? But let's do first at least one or two examples on this. Example number 1, f of x equals, for example, x over x plus 3 times x minus 4. If they ask you find the vertical asymptotes in this function, what you do, set your denominator equals 0, x plus 3 times x minus 4 equal to 0. From here, x plus 3 equals 0. And here x minus 4 equals 0. X plus 3 equals 0, it means x equals negative 3. And x minus 4 equals 0, it means x equals 4. We call these two actually the vertical asymptotes, which you learned also in college algebra, correct? When you were dealing with rational functions in college algebra, you know how to find the vertical asymptote already. Now, if I want to just graph these vertical asymptotes, I'm not going to graph the function, correct? If I just graph these vertical asymptotes for you, for example, here I have negative 3, here is 4, and if I draw the vertical asymptotes, right? I have a vertical asymptote at 4, and I have a vertical asymptote at what? At negative 3. Now, you see, if you pick up a test point, if you do a sign analysis, we call it sign analysis. If you pick up a number from negative infinity to negative 3, this interval, right, on the left side of negative 3. For example, negative 4, right? If you pick, for example, negative 4, and you plug to your function negative 4, let's see what's happening. What is the sign of the function there, correct? Let's do this actually. Let me plug in for you. Your function is x over x plus 3 times x minus 4. Let's plug in negative 4. Then this one will be negative 4 over negative 4 plus 3 times negative 4 minus 4. Numerator, I don't really care about what is the number, right? I told you I'm doing sign analysis. Numerator is negative, a negative number, which is negative 4. Denominator, negative 4 plus 3 gives you negative 1. And negative 4 gives you negative 8. Negative times negative gives you positive, right? And negative over positive gives you what? A negative. It means here the sign, the function is, the sign of the function is negative. That means the function likes to go to negative infinity actually like this. Correct? Another critical point is 0, you see, because if you plug in 0, it becomes 0 over 0, correct? Which is, this is another critical point. Now, pick up a number between 0 and negative 3. For example, negative 2 or negative 1. Let's plug in negative 1, for example. Negative 1 over negative 1 plus 3 times negative 1, negative 4. Numerator, again, negative, denominator. Negative 1 plus 3 gives you positive 2 times negative 1, negative 4, negative 5. Positive times negative gives you negative, right? Negative over negative gives you what? Positive. It means here your function actually would like to go up to positive infinity, right? Same way, if you pick up another test point from 0 to 4, for example, let's say 2, correct? If you plug in 2 there, it will be 2 over 2 plus 3 times 2 minus 4. Numerator positive, denominator becomes what? 5 times negative 2, negative. Positive over negative gives you negative. It means here your function likes to go to negative. And same way you can do a sign analysis between 4 to infinity, right? For example, 5. If you plug in 5, you will see your function again likes to go to positive infinity. When you do vertical asymptote, it doesn't matter, but if I give you such a problem, if they give you such a problem, for example, in this example, limit of x cubed over x squared minus 1 all square as x approaching to 1. If they ask you to find this limit, right, the best way to find this limit is, okay, where are my vertical asymptotes? It means I'll set my denominator equal to 0. X plus 1 times x minus 1 equals 0, right? From here, x equals negative 1. From here, x equals 1. I have a vertical asymptote at x minus 1, and I have another vertical asymptote at x equal 1. Now, if I draw my number line, and I put here negative 1 and put here 1, and I draw my asymptotes, right? This is one of the asymptotes. Here, the second asymptote. And this problem, because I'm dealing with limits, I don't care about negative 1. I don't want to study this part because why? Here you see, as x approaching to 1, that's important to me. What the limit of this function does when you are approaching to 1, correct? Again, I will do my sign analysis between 0 and 1, and from 1 to infinity. I'll plug two numbers in my function and I see what the function is doing actually. Going to positive infinity or going to negative infinity? Maybe one side negative, maybe one side positive. I don't know. Let's plug in those numbers, correct? For example, between 0 and 1, I can put 0.5, right? Then it will be 0.5 cubed over 0.5 square minus 1 all square. Again, no need to calculate these numbers. The important part is sign analyzing. The numerator is positive. Denominator, whatever I get inside the parentheses, even if it's a negative number, after I square it anyway, it gives me positive, right? That means from 0 to 1, the function would like to go to positive infinity like this. Also, if I plug a number, for example, 2, it will be 2 cubed over 2 squared minus 1 all square. Again, you see I'll end up with a positive sign. That means my function goes to positive infinity. Now, is the limit exist here? Yes. How much is the limit? Immediately for that problem, you can write, okay, I have limit of x cubed over x squared minus 1 all squared as x approaching to 1. Then my answer is what? My answer is infinity. But if one of them goes down, one of them goes up, on that time you say the limit does not exist, remember? Because both of them is not going to one way, one down, one up. On that case, you will say, oh, the limit does not exist. These were the topics that actually we covered in chapter 1, right? Now, bringing those back, those ideas, let's find answer to this question. What happens as x approaches to positive or negative infinity? Let's find an answer for this question before. X approaching to a number, but function is approaching to infinity. Now, what happens if x approaches to infinity? What the function will do? That's the topic of discussion in this section, correct? Let me write two examples. Limit of 1 over x as x approaching to, for example, let's say infinity, positive, and limit of 1 over x as x approaching to negative infinity. Let's solve these two examples. To solve these two, to find a correct answer, let's use the table method. Here x, here f of x. Let's plug in few points in our function and see what the function does. For example, 1, let's use 10, 100, and maybe 10,000, or maybe a million, whatever. When you plug in 1 to this function, you have 1 over x. 1 over 1 gives you 1. When you plug in 10 in this function here, it will be 1 over 10 means 0.1. When you plug in 100, it gives you 0.01. And if you plug in 10,000, it gives you 0.001. Correct? What do you see? As x approaching to infinity, as this number is growing bigger and bigger and bigger. For example, this time I'll put a million, right? Then the answer will be 0.00050, then 1. You are going closer and closer and closer to which number? To 0, right? 0.0000001 is really a close number to 0. Then the answer for this limit is actually 0. Let's check with the other one. X, f of x, because x is approaching to negative infinity, I'll use the same numbers with negative sign. Negative 1, negative 10, negative 100, and negative maybe 10,000, and so on. Of course, here I'll get negative 1, here negative 0.1, negative 0.01, negative 0.0001, right? Again, you see, as x approaching to the left, to the negative infinity, your function is approaching to what? To 0, correct? We call that actually y equals 0 is a horizontal asymptote, correct? This is the way that you find horizontal asymptote, or in general, let me put some definitions for you here. If f of x gets really close to a certain number, as x approaching to positive or negative infinity, then the limit exists, right? Then you can say limit exists. You see, your limit is 0, right? Your limit exists. And this limit, we call it what? Horizontal asymptote. Hopefully, I could explain it well to you. Now, let's focus on this example. For example, if I have limit of 1 over x to the power of n as x approaching to, let's say, positive infinity. What's happening? How do you find? Can I rewrite this one based on the definitions or rules of the limit as a limit of 1 over x as x approaching to positive infinity, then all to the power of n. We learned this rule in chapter 1, correct? The n side, I already know the name, or I already know the value. Limit of 1 over x as x approaching to positive infinity gives me 0. Then 0 to the power of n, which gives you what? 0. What does it mean, or how I can translate this in a simple English language? That any function that's in the form of a constant over a variable, it doesn't matter your variable, which power of your variable, as x approaching to positive infinity, and you take the limit, if your x approaching to positive infinity, even negative infinity, plus minus, both of them, always your answer is what? 0. We use this rule a lot when we are dealing with limit and infinities. Just remember there, a constant, for example, 2, over a variable to any power, if you take the limit of it and x is approaching to positive or negative infinity, the answer is always what? 0. This is what we use. Any constant, correct? Now, let's do an example. Let's start with examples. There are different methods of them. At least I'll try to introduce 1 or 2 of them or 3 of them for you. How you deal with limit and infinity, or how to find, when you say limit infinity as x approaching to infinity, it means how you can find the horizontal asymptote for a function. Example number 1, find the limit of 5x minus 2 over 3x plus 9 as x approaching to, for example, positive infinity. Look, immediately, if you plug in infinity to your function, it gives you 5 times infinity gives you infinity, infinity minus 2 gives you infinity. And 3 times infinity gives you infinity, infinity plus 9 gives you infinity. Please do not tell me that the answer is 1. Infinity over infinity is 1. No, it's not that simple, right? Something is wrong. We don't know how much is infinity, and we don't know how much is infinity in denominator. It's just a symbol. You cannot cancel it like this and say, oh, the answer is 1. No, that's totally wrong. You see, infinity over infinity is one of the forms of the limit that's not simple. We don't have an answer for it. We have to simplify it. Later in Calc 2, we will teach you a method using derivatives, how to deal with these forms. But right now, we give you another simple method, how to deal with this problem. It means we cannot deal with infinity over infinity. I have to find an algebraic way to get rid of this infinity from the denominator, right? It doesn't matter what I have in numerator. Denominator, I have to get rid of that infinity. Look, based on, if I have a fraction, for example, a over b, if I multiply a number in the numerator and if I multiply a number in the denominator, it doesn't change anything in a function, right? It was a very simple rule of fractions. Or if I have a fraction and I divide the numerator and denominator by a number, again, it doesn't change the value of your denominator, correct? You learned this rule in grade 5 or 4 or 6 when you were in school, right? Let's use this technique and let's see what we can do here. I have limit of as x approaching to positive infinity. What I do here, let's divide all the terms in the numerator and all the terms in the denominator. let's divide it by x. Later, I'll explain why x. Let's divide everything by x, right? Here, 2 divided by x. Here, 3x over x. And here, 9 over x. Let's see what's happening. Let's simplify. Then limit, fraction bar, 5x over x gives you what? 5. Minus 2 over x stays the same. Now, 3x over x gives you 3. Plus 9 over x, as still you have x approaching to positive infinity. Now, based on the rules of the limit, can I write this one as a limit of 5 as x approaching to positive infinity minus limit of 2 over x as x approaching to infinity over limit of 3 as x approaching to infinity plus limit of 9 over x as x approaching to where? To infinity. Now, limit of 5 as x approaching to infinity gives you 5. What is this limit? Limit of 2 over x as x approaching to infinity. We just discussed this part becomes what? 0. That means 5 minus 0 over limit of 3 gives you 3. Limit of 9 over x as x approaching to infinity is again what? 0. 3 minus 0. What is 5 minus 0 over 3 minus 0? It gives you 5/3. Correct? It means the value of this limit is 5/3. What does it mean in graphing? Y equal 5 over 3 is your horizontal asymptote. Right? For the given function. If it is a function, if it's not a limit, they just give you as a function this problem. The y equal 5 over 3 will be your horizontal asymptote. Correct? Not that difficult. Now, what I did, which method I used here, I divide every term by the largest power of x, or in general you can say variable and denominator. This is your method. Which kind of problem they gives you? One of the methods to deal with limit at infinity, what you do, you divide your numerator and denominator with the highest degree or highest power of denominator, and you simplify your limit. Correct? Let's do another one to explain more that method for you. Same thing. Limit of 5x squared minus 4x over 15x cubed minus 3. Or maybe they don't give you as a limit this problem. They can as x approaching to negative infinity. Maybe they give you as a f of x equal this, and they ask you find the horizontal asymptote. As soon as they say find the horizontal asymptote, take the limit x approaching to plus minus infinity, right? Okay, based on my method, I have to divide all terms by the highest exponent and denominator. What is the highest exponent and denominator? Is x cubed. Let's do it. Keep your limit. X approaching to negative infinity. Fraction bar. 5x squared. Divide by what? Highest exponent. Even I'll change the color for you. By x cubed. Minus 4x over x cubed all over 15x cubed over x cubed minus 3 over x cubed. Why the highest exponent and denominator? Because usually denominator is a problem for us, correct? We cannot have 0 in the denominator, correct? That's why your focus is on the denominator. Now let's simplify, correct? Then limit fraction bar x approaching to negative infinity, 5x squared divided by x cubed gives you 5 over x minus 4x divided by x cubed gives you 4 over x squared. 15x cubed divided by x cubed gives you 15 minus 3 over x cubed. I will not show again the limit of each one, right? In previous problem, I did all. Now, if you plug in negative infinity, limit of 5 over x as x approaching to negative infinity gives you 0. It means this part becomes 0. Also, this part becomes 0. It means 0 minus 0 over 15 minus 0, which gives you 0 over 15, which your answer is what? 0, correct? It means your function y equals 0 as your horizontal asymptote for the given function, correct? One more example. Then I'll jump to the next form. Limit of 7x cubed minus 2x squared plus 1 over 9 minus 2x as x approaching to negative infinity. There is a shortcut. I didn't introduce that shortcut for you, and I'm lucky that your book is not explaining that shortcut for you. Why I'm not giving you that shortcut? Because sometimes you lose the focus and you give me a wrong answer. That's even I didn't discuss that with you, but there is a shortcut that even by looking to the problem, you know the answer, but I don't want to explain it, right? If it was a face-to-face class, maybe I will, but right now, no, because I'm away from you. And if you use that method, maybe you do a lot of mistakes. That's why I didn't explain, but why I'm raising this issue, why I'm telling you, maybe because when you get in touch with some tutors or friends, they tell you, oh, there is a shortcut, why your professor didn't give it to you. There is a shortcut, but I don't want to explain it because you need a lot of practice to understand that. That's why you're new. I don't want to give it to you, correct? Let's do our way. Okay, now, what should I do? I will divide each term by the highest exponent in the denominator. The highest exponent in denominator is x, right? Then I can write limit as x approaching to negative infinity, fraction bar 7x cubed divided by x minus 2x squared divided by x plus 1 over x all over 9 over x minus 2x over x. Simplify, limit x approaching to negative infinity, 7x cubed over x gives you 7x squared minus 2x squared divided by x gives you 2x plus 1 over x over 9 over x minus 2. Okay, now, when you plug in negative infinity, correct, this part becomes what? This part becomes negative infinity, correct? negative infinity minus negative infinity plus 1 over 0. It means your numerator becomes negative infinity. What about denominator? This part becomes 0 and you end up with negative 2. What is negative over negative? Gives you positive. Infinity over 2 gives you what? Infinity. That's the reason, because if I introduce the shortcut for you, immediately everyone will tell me, oh, the answer is negative infinity. They don't focus on this part, that the sign is changing to positive infinity. This is one of the common mistakes, the people who are using the shortcut, correct? One more example, then I may stop the lecture and I jump to the next section. Let's focus on this example. Which one? Example, limit of x squared plus 2, square root of x squared plus 2 over 3x minus 6 as x approaching, for example, to positive infinity. What you do? Apply your method, divide everything by x. But I want to explain something here for you. Limit. Numerator will be square root of x squared plus 2 over what? Over x. Denominator, no problem. 3x over x minus 6 over x is still x approaching to positive infinity. Look at your numerator. Here you cannot write this one as a square root of x squared over x. You should find a technique or a method that put this x also under the square root. What should you do? Again, unfortunately, it's not a face-to-face class. We cannot discuss a lot. I will explain everything here again to you. What you do, look, you put the x under the square root, but you make it x squared, because x is actually equal to square root of x squared. Is this true? Somehow it's not true. This one is true. Absolute value of x equals the square root of x squared, right? But in your book, they don't show this part that it should be actually absolute value. It's really important. In some problems, you're changing the sign, but here in your book, immediately they mentioned, okay, bring the square root, the x under the square root, and you divide everything under the square root by x squared instead of x, plus 2 over x squared, because of this, right? Denominator, you have 3x over x minus 6 over x. Still x approaching to infinity. Now you see, limit square root of x squared over x squared gives you 1, plus 2 over x squared, all over, here it gives you 3 minus 6 over x as x approaching to where? To infinity. When x is approaching to infinity and you have limit, this part becomes 0, this part becomes 0. It means you end up with the square root of 1 over 3 minus 0, which gives you 1/3, right? Your answer is what? 1/3. One more example, I'll just tell you the method, then you do it by yourself. It's a calculus class, you don't need me to do everything for you. For example, look at this problem. Limit of a square root of x to the power of 4 plus 2 outside minus x squared as x approaching to positive infinity. Look, if you plug in infinity immediately here, you end up with infinity minus infinity. And please don't tell me infinity minus infinity is 0. No, wrong. correct? It's another form of the limit that you have to deal with. We don't know the answer for negative infinity minus infinity. And these kind of problems, what you do, you multiply by the conjugate of the given function. I'll just do two steps of it and I'll let you do to complete the example, correct? What I do, I'll do this. Limit square root of x to the power of 4 plus 2 minus x squared. Actually, what is the denominator here? Can I put a denominator of 1 for it? Definitely, no problem. Times, what is the conjugate of numerator? The conjugate of numerator is the square root of x to the power of 4 plus 2 plus x squared. And same thing, you multiply with the denominator, square root of x to the power of 4 plus 2 plus x squared denominator. Now multiply the top, multiply the denominator, and after that apply your rule. Divide by the highest exponent of denominator, and your answer should be 0 at the end, correct? If you have a problem, next day, next office hour, you can ask me how I did this example and I'll explain it to you if you cannot find the answer. And let me tell you that my office hour time will change. For your class, it will be Wednesday, whatever, I have to check which class you are. I will announce my new office hours for you because at the time that I had office hour, except 1 or 2 days, that few students came online, the others, they didn't show up. I know it's really easy. Most of you don't have problem, but I will bring a little bit change in my office hour and I will let you know. This was all about section 3.4, which is finding horizontal asymptote. I'll stop the lecture here and see you in lecture 3.5.